Hi everybody, back to our YouTube Cook RT again. Today I'm going to finish up what I left over talking about last time I talked about our uh, uniform plane wave. So this one I'm going to talk about the oblique incident of the plane waves. Uh, Last time we talking about a normal incident plane wave. What does this mean is when we have our boundaries between the media number 1 and media number 2, and then you have our electromagnetic wave propagating to the surface or to the boundary, and then this make the anchor 0 degree of the what we call normal line. So this is normal line here, but for this one we're going to get more complicated, because the wave that are incident on the boundary is not making anchor like 0 or normal to the surface, but it's going to be have some degree of incident, like this one here. Okay, so it's pretty much based on the principle, just like last time, of the normal incident plane wave. But this one is going to get involved in more equation of what we call a Snell law. Okay, what you need to find is you need to find uh, the transmitted anchor, or we call the reflection and reflected anchor. Okay, so just let's take a look at the page number 1. What I have here is that it's look much better from the diagram here. So when I have the media number 1 and media number 2, and the red line represent the boundary of two meteors, I have our incoming electromagnetic field, or incident electromagnetic field, and then reflected, and represented by EMR, and also a transmitted electromagnetic waves like represented by EMT. And what gonna happen is you have like incident anchor theta I, and reflected anchor is to be equal to incident anchor theta I. But when you are the electromagnetic wave get into the different media, your the electromagnetic wave is going to reflect, not reflect, but reflect, and make the anchor of the normal line to be theta 2. And it's coming to the Snell's law that help us to find theta 2 when theta I is known, right? So the Snell law states that psi theta I over psi theta t is going to be equal to beta 2 divided by beta 1, or simply is this equation beta 1 psi theta I equal to beta 2 psi theta 2. And since we're talking about a case of lossless media, or sigma or conductivity is equal to 0, so you just ignore the real part of grammar of propagation constant, and what left over is beta, which is equal to omega square root omega epsilon, which I mentioned in the previous YouTube. And then you represent beta 1 by square root of mu1 epsilon 1, and beta 2 is the square root of mu rho epsilon 2. And from this equation you'll be able to find theta 2, or the transmitted anchor, to be n1 over n2 multiplied by psi theta I. And this one I represent square root mu1 and epsilon 1 is the to be your index of reflection. And then if you consider from the equation here, you know that your psi theta is in the range of -1 to 1. It cannot be greater than 1, or cannot be lower than -1. So in case of where eta 1 is greater than eta 2, I'm sorry, n1 is greater than n2, you're going to end up with theta 2 is greater than theta I. So it means that this one is going to get the anchor is going to get bigger and bigger. And what happened is that for somehow, or when you increase the incident anchor here, it's going to have a transmitted wave, parallel to the boundary. And in that case, your theta 2, you represent theta 2 by 90 degree, and you can find theta I simply become from this equation. When actually you can pick up this equation here. When you assign theta 2 equal to 1, so your theta 1 actually this one I put something wrong here. It's supposed to be the psi theta I, correct? It's going to be n2 over n1, and you can find theta I, which one this one is going to be what we call critical angle. So what happened in the case if we increase the incident angle just right here, is making more than critical angle theta C. What happened is that it's going to be is no transmitted electromagnetic waves at all, but all of them is going to reflect back to the media number 1. Okay. And for the case that sigma is not equal to 0 or lossy media, you still have to keep your grammar equal to alpha plus j beta, so you cannot ignore the real part or alpha or attenuation constant. But we're not getting into this one here because I want to explain the basic principle of oblique incident plane wave. Now we have two types of polarization. If we are looking for reflection coefficient and transmission coefficient for the lossless media or sigma equal to 0, your rho or perpendicular polarization, that means your electric field is going to be parallel in boundaries, and also have parallel polarization, that means your magnetic field is going to be parallel to the boundaries. Okay, so it should not be so difficult for you to understand. And without any proof, by using math, I'm going to show you the equation is going to get into be more complicated. So for perpendicular polarization, your rho perpendicular is going to be your eta 2 cosine theta I. But it still becomes the ratio of the reflected electric field divided by the incident electric field. And for transmitted coefficient, transmission coefficient still become 2 eta 2, but you have some factor of cosine, of incident angle and transmitter angle here, and that still become the ratio of transmitted electric field and incident electric field, and the relation 1 plus rho perpendicular equal to tau or perpendicular, still applying. So you look at this case when you're talking about a normal incident plane wave. You have the incident plane wave here, and you know that your theta I simply becomes 0, so this term become 1, and it's 1 1 1. It just come back to the equation of your reflection coefficient of the normal incident plane wave. Simply become eta 2 minus eta 1 over eta 2 plus eta 1, right? And this one is still the same. It's drop out to be your 2 eta 2 over eta 2 plus eta 1. But for the case of parallel polarization, it's going to be your different equation for reflection coefficient and transmission coefficient. take a look at this one here. You have eta 2 cosine theta I for perpendicular polarization, but for parallel polarization is similar to like switch around here. So this one turn out to be what, eta 1, right? And this one still become a cosine theta I, and this one still become a cosine theta t, but this one become eta 2. Okay. The other thing is like the relation between the refraction coefficient and transmission coefficient for the parallel polarization is not the same as the perpendicular polarization, because you're going to have the term of I have some problem here because you cannot see here when I scan it. It's become a 1 plus rho of parallel equal to tau parallel, but still have to multiply by cosine let me get this one, theta t over cosine theta I. Okay, so what I'm missing here is like cosine theta t over cosine theta I. And you know that you can calculate when you know theta I. You can calculate for theta t simply by using Snell law, right? N1 sine theta I equal to N2 sine theta 2. Okay, now let's write equation for electric fields and magnetic fields. There's something that I would like to point out, So for the perpendicular polarization, this is the electromagnetic wave is coming in this way here. It's shown by the arrow and reflected back. So you look at this one. For the component of electric field, they all have the component in their y, axis, as represented by the rectangular coordinate here. This is x, this is z, and this is y. It's like get into the paper. So you can use your right hand rule to find the relation of what's that, p, which is the direction of propagation or the direction of electromagnetic wave, equal to E cross H. Alright, hopefully you not forget about that one. This is very important. So that's why for electric field you have components to become AY, AY, all AY, and it's still in the positive AY because you have no negative at all here. Okay, so let's start writing our equation for electric field. For EI, if I put the amplitude to be EI0 starting and then multiply by exponential, it used to be negative gamma z, right? But since the electric field has the component in both x and z, right? If you take a look at this one here, because y is like go to this direction in the paper, so you have to rotate this one around to see that your electric field has component in x and z. Sorry, I take it back. It says the component of y, component only, but the direction of the wave, the electromagnetic wave propagate is in the plane of x and z. That's why you have x and z here, right? So or you have like x and z. This is show you the direction of propagation. Even for the magnetic field, you still have x and z, right? Now you take a look at I'm not getting into how to get this one here, but actually I can show you a bit how to get this one here. Alright, for EI you see the direction of propagation, which is in the plane of x and z. So you can find this is the, when you take this one to be angle theta, right? You have to go back and think about it. So you can talk about axis of the propagation to be x and z, but for this one it's going to be just like a vector, so it's going to be the component of z and x. So they're both going through the positive direction of z and x, and then this vector is simply cosine theta I for z, right? So I have the cosine theta I z. For x, it's going to be sine theta I. Okay, just let take a look at that way. And now for ER, it's become our amplitude of reflected wave, reflected electric field. And then now you take a look at this one here, the direction of propagation. You have ER here, so your ER just come to play on this way. Now you take a look at the because ER is parallel to the boundaries, it still has the component x and z. Sorry, the direction of propagation still have the in the x, y, x, z plane. So that's why you have this become still have x and z. But you take a look at the negative side here. It tells you that it has a component in the negative side, negative sine theta I multiplied by x, because you take a look at that carefully, the direction of propagation is going to go this way, right? So you have component of the negative x direction and the positive z direction, and then that's why your z have no the sign in front of cosine theta I still become positive, but this one become negative, right? And for ET has the same direction of the x and z component of the propagation direction is still like the incident electric field. Okay, so that's why you have this one to be similar. I mean, I'm talking about a sign, but since you are in the meter number 2, you have to represent theta I by theta t, and this one also theta t as well. And your beta 1, you have to represent beta 1 by beta 2, because this is in the media number 2. Okay, and the relation here for in the case of your sigma equal to 0, and then the magnitude of reflected electric field still become rho multiplied by ER0, and the same thing as the transmitted electric field is equal to ER0 multiplied by our transmission coefficient. And now you can write HI in the term of E, right? You pick up, because you have the relation E over H equal to what? Equal to eta, right? So that's why you have H equal to E over eta. So this one is still meter number 1, so you have to divide by eta 1, and HR in the meter number 1, you divide by eta 1, but HT is in the meter number 2, you divide by eta 2. And now you take a look at H. It's not just like electric field that have the Y component only, but for H is in the X and Z plane. Okay, so you have both component of AX and AZ, so they all have the AX and AZ. Alright, but for this one, the direction of propagation, this one still applying, right? The same thing here. And for HR, it's look like exactly this term. It's supposed to be have negative sign, and this one is look exactly like this term. And now you take a look at the component of HI. Where is HI? Look at this one here. This one is x and z. So you know that your h is going to this direction here. So the components simply become this vector plus this vector. Okay. So that's why you have our negative ax and you have a positive or az. Correct? Easy to take a look. So this becomes cosine theta I plus sine theta I. Now you can tell what is your HR. Your HR is going to this direction here. So you have the component of positive x plus the positive z. So that's why you have the positive sign here of x and you have the positive sign here of a z. Okay, so the factor in front of ax to become the same, right? Cosine theta I, and this is sine theta I. Exactly the same thing. Now you can tell of your ht, right? Going to be the same because it's become two vector. One is go to a negative ax and one is go to a positive az, sorry. So that's why you have a negative sign in front of ax, but for az is to become positive and the rest to be the same, except this is in the median number 2, so you need to use the theta t instead of theta I, and also this term. And this one eta 2, I already explained that. And this one, don't forget to change it to be your beta 2. Okay, so just give you an idea about it. And now take a look at the parallel polarization. You have ei, since the h in parallel with the boundary, so hi still have the component in y direction. They are all the same. Alright, you can take a look at the hi first. This is the direction of propagation, and then you compare above here. It's look the same, right? And also this one her, this is hr. Still apply to this because you're talking about electromagnetic wave. You're not talking about a component of electric field or a magnetic field, so they all have to be the same here. Alright, so this is the ei 0 over eta. This one have to be eta 1, and then hr, this is er 0 to divide by eta 1, but ht has to divide by eta 2. Now what about ei? Same as I explained to hi of perpendicular polarization. You can think about it. And this one, you take a look at this one, still be the same, right? What is your ei here? You take a look at this one. This is the positive x direction and this is negative z direction, right? Because I already define the rectangular coordinate system just like this one here. This has become positive z. So you look at this one. What happened? For ei is going to this way. So you have the component at positive ax and then minus minus on the negative az direction. So that's why you have negative sign in front of az, but for you have positive sign in front of ax. What about your er? You take a look at this one here. In fact, this one is simply the two vector add up to make er. So it's going to the negative x direction, and then also go to negative z direction. So you have er. So I did something wrong here. It's supposed to be a negative and negative here. And what about et? Et is what? Et is the two vectors add up. So this one become a positive x, but it's going to that direction. It's become a negative az. That's why you have the negative sign in front of az. All right. Just give you the rough idea about how to write our fields equations. Okay, the next one, the interesting one, is the Brewster anchor of total transmission. What does this mean? Actually, it's going to be the opposite of our Snell's law. For the Snell's law, you try to find what incident angle to make it to be your total reflection, right? No transmit at all. But for Brewster angle, it means that what is your incident angle to make all the electromagnetic waves, transmitted into the medium number two without any reflection. So when you're talking about no reflection, that means your rho, the reflection coefficient have to be zero, right? So I pick up two cases. One is perpendicular polarization, and you already have our equation for rho, right, in the previous page. This is reflection coefficient. This is for perpendicular, and this is for parallel polarization. So for the perpendicular polarization, you have you want this one to be zero. So that means this term, the nominator, has to be zero, and same as the for parallel polarization, and this term has to be zero, right? So you can find what theta I. So that's why what I have here. So you can use the simple math to solve the problem, right? Because you already know where theta I. If you're looking for theta I, and you want to find theta t, and you also use the Snell's law, beta 1 sine theta I equal to beta 2 sine theta t, and then you can write your theta t in terms of theta I, and in that case you can find your theta I. Okay, so use the simple math. Same thing as the parallel polarization. Okay, let's take a look at the example for the Brewster angle here. You have media 1 is free space and media 2 is grass, and you have a relative permittivity to be 4 and relative permeability to be 1. For the case of polarization, if you're looking for Brewster angle, you simply apply the equation that the reflection coefficient have to be 0, and you end up with eta 1 cosine theta I equal to eta 2 cosine theta t. And also if you're looking for theta I Brewster angle, so you need to write theta t in the term of theta I. Okay, this is there's some equation that you can find theta b of Brewster angle directly from epsilon and mu, but for this one I just show you you can also use only two equations here. One is the reflection coefficient equal to be 0, and then the Snell law, two equation you can find also a Brewster angle. Well, we are looking for theta t in the term of theta I. So from Snell law, you can find theta t, right? Simply become n1 over n2, and then multiply by theta I. And in this case, your n is the index of reflection, which is equal to square root mu epsilon. So what you have left is the square root of mu r1 epsilon r1 divided by square root mu r2 epsilon r2, because you have the other one, mu 0 and epsilon 0, they are cancelled out, right? So you plug in the number epsilon 2 equal to 4, so you ended up with sine theta t equal to sine theta I over 2. And now you have theta t and in the term of theta I, but since this one is like you're talking about cosine, so I'm gonna convert sine to be cosine. Use the property of cosine theta t equal to square root 1 minus sine square theta t. And since your sine theta t is equal to sine theta I over 2, I represent sine theta t by sine theta I over 2. And then you have also change the sine function here to be cosine, simply become 1 minus cosine square theta I. Okay, and then from this equation here, now you can write your theta t in the term of cosine theta I, and that's why I put this term here. And then you square both sides of the equation, and this is just simple math you can work out by yourself. And finally I have cosine theta I equal to square root 1 over 5, and you can find theta I, which is the Brewster anchor, to be our cosine square root 1 over 5, which give you 63.49 degree. Okay, so again, Brewster anchor, you're looking for the incident wave with the anchor theta I. Let's make your electromagnetic wave totally transmitted into the medium number 2, which is opposite of the Snell law. Oh no, sorry, which is the opposite of critical anchor that you want. It's become totally reflected, from the boundary between the medium number 1 and medium number 2. Okay, the other one is interesting is polarization of uniform plane waves. I just give you the simple explanation. When you write electric field or magnetic field, in cases they have like at least two components. For this one you have a x component and a y component. What can you have is that you have the amplitude of the x component of electric field and y component of electric field, and also you can have the phase difference between the component in the x and component in the y, right? There's only two factors that you have to consider. And the same thing as the magnetic field, you know that this is H equal to E over eta, so simply divide the component y and x by eta. Well, you take a look at this one. So for electric field, let's have our x component and y component. What you need to compare is that you need to compare EM1, the amplitude, and the phase only. Okay, what you need to do is just compare the amplitude EM1 and EM2, and also the phase. Right? Take a look at the case 1. If you have the phase, this is important. Theta equal to 0, so you can pick up this one here. So your EX is equal to this term, right? And this is EY equal to this term. So you know that cosine is going to be cancel out when you divide EX over EY, right? You end up with EM1 over EM2, and your EX equal to EM1 over EM2 EY. Or you can compare X equal to MY, which is the linear. And if your EM1 not equal to EM2, you can find the anchor, tan theta to be EM2 over EM1, which is linear. So you know that, what is the slope of the line, or it's become a linear polarization. Now take a look at the theta equal to negative 90 degree. If you know why I pick up theta equal to negative 90 degree, because take a look at this one, x component and y component of electric field. When you have our theta to be negative 90 degree, what happened? You know the property cosine A minus 90 degree equal to cosine A cosine 90 degree plus sine A sine 90 degree, and cosine 90 degree is 0. So is simply cosine A minus 90 degrees become sine A. So this term is dropped out to be a cosine omega t minus beta z. That's what I have it here, right? And you can tell the relation if you are ex square over emi square, which is cosine square, right? And ey over em2 square is going to be sine square. And when you add them up, you know the property cosine square plus sine square equal to 1. So this is simply become look like something or some kind the equation that you familiar. So what happened is that if em1 equal to em2, this is going to be your circle equation, right? But if em1 not equal to em2, it's going to give you ellipse. And since theta equal to negative 90 degree, so when you rotate, it's going to be give you the clockwise rotation. And this one we call right hand polarization. But if it happen that the phase difference to be a positive, that means it's going to in counterclockwise, and it gives you the left hand polarization. Okay, so hopefully I give you some basic idea about oblique incident of uniform plane wave. I'll see you in the next YouTube.